as much as I would have liked this to have been a code-along demo of the DKIST user tools, unfortunately things are not quite ready for this, so I'm going to demo these at you. But I have been working for the last couple of years in writing Python user tools that my objective is to make it as easy as possible for you to find, download, load into Python DKIST level 1 data, right? Load into Python is about where I stop. There's visualization, a couple of visualization helpers and some stuff, but basically get the data into Python and let you use Python to do your data analysis. As Alistair mentioned earlier, this is written in Python, not in RDL. So, as I just kind of said, this is like the list of stuff that this package and these user tools are trying to achieve. I'm not here to write analysis code for you. You can. It's your job, not mine. So there'll be search, download. I will demonstrate download. Search does not exist yet. Loading, I'll show you loading. There's built-in coordinate systems and stuff that I will give you a quick demo on as well. And basically the idea is to get the data into a form where other Python packages will accept it and let you work with it. So Fraser and Alistair kind of alluded to this earlier, but the layout of the DKIST level 1 data is a little unusual. Each data set comprises many FITS files. Each FITS file is like one calibrated frame of data. Getting into the nitty-gritty of what that means is a little bit interesting, but basically it means for VBI, VISP, and Cryo and VTF, each FITS file will be a 2D array, give or take. And then for DL, it may be 2D or maybe 3D, we're not quite sure yet. So if you have a long VTF dataset, for instance, you can very quickly end up in tens or hundreds of thousands of FITS files per level 1 dataset. As was also mentioned earlier, each of these FITS files will be self-consistent and will contain all the metadata you need, both for that individual FITS file and also information about where that FITS file lives in the large collection. So I have some demo data that's based on some SST crisp data. My test demo dataset is 9,728 files long. These are just file names. So one of the first things we end up doing is trying to take these like lots and lots of frames and stack them into a cube, because I'm assuming that's the way that most people would want to interact with them. However, reading 100,000 FITS files, even if you don't touch the arrays, just reading the headers is going to take some time. Reading all of the arrays and rewriting them into one big array on disk is going to take a lot of time. And a lot of memory as well, probably. So the first and biggest challenge that the user tools it is designed to solve is to work out how to interact with like 100,000 files in one go, right? And the answer is to open them as infrequently as possible and keep them open as little as you can. So while I could take the 100,000 FITS files, read all the headers, work out how they stitch together into a cube, and then expose you a cube, the origin of the asdiff data format that Alistair spoke about earlier was a way of not having to read all the FITS headers to work out how to stitch the FITS files together, right? So the asdiff file contains four main things. It contains the ordering of all the FITS files and where they go in a higher dimensional cube. It contains a WCS object that gives you the physical coordinates for all the pixels in that reconstructed higher dimensional cube. It contains a table of all the headers in all the FITS files. And it also contains some extra metadata about the data set, which is going to be basically identical to what's stored in the data set in the data center for what you search against when you search for data sets. The idea of putting all the FITS header in this is that it will allow you to do metadata studies or search through a catalog on your computer. I haven't implemented it yet, but the idea is that the user tools will provide you a way of searching through all your local data as well as all the data that is on at the data center. So if you downloaded a load of ASDIF files from the data center and you cared about all of the frames that contained one particular header value for some reason, I don't know, you wanted every exposure that was exactly 3.2 seconds long or something, you'd be able to search for that through the user tools. In theory, it does not exist yet. So somebody asked earlier what these ASDIF files look like, and the answer is they look like a lot of YAML. So this is like standard YAML header block. It tells you what it is. It tells you what version of ASDIF that it write with. You'll notice that all of the versions in here are all dev. This stack is still like just Git repos all the way down, which is one of the reasons why I didn't get you to run it, because it's a pain to install. This will obviously be fixed when it's more ready. So it tells you what version of ASDIF wrote the file. It also tells you what version of all the extensions you used to write the file, and then it contains many more lines of YAML. These are the references to the FITS file. So this is like a 3D nested array of references to FITS files, basically. And then it's also got the GWCS object, and then the header table. The header table is stored in binary at the end after the YAML to speed things up, basically. Yeah. GWCS. I'll come back to GWCS. So we have this dataset class in the user tools package. Just actually, I meant to do this at the beginning. Hands up who uses Python on a regular basis. Okay. Hands up who uses IDL on a regular basis. Okay. Yeah, that's fine. Interesting. So I have a directory on my laptop here, which is this SST dataset. I load that directory into this dataset class, and now the dataset class knows about itself. So this dataset I've got here is 4 by 128 by 19 by nearly 1,000 by 1,000. It's float 32. And it has this chunk size property, which means that each file is 1,000 by 1,000, and each chunk is its own file. So if you multiply these three numbers together, you get about 9,728. It also knows what the axes are. So the axes here, the pixel axes here are Stokes, scan number, wavelength position, and XY spatial. So this is a VTF-like data set. And Stokes, time, wavelength, latitude, longitude, the world axes. As I mentioned earlier, it also has all the FITS headers. So there is a many column by 9,000 row table of FITS headers in the ASDIF file. So all of this that I've shown so far has not opened a single FITS file at the moment. This has all been done off of the ASDIF files. We haven't opened any FITS. There's also a meta dictionary, which has some extra information that is probably mostly not useful to end users, but will be useful to the user tools. So the idea then is once you've got this data set, you can subset it. You can slice it. Those who are used to dealing with Python will appreciate this is just array slicing syntax. It's reasonably similar in RDL, if I remember correctly. So I'm picking out the first Stokes component and the first time step here, the first wavelength scan. So now the data set is 19 by 1,000 by 1,000, and it's wavelength position, space X, space Y. Okay, so how do we do the actual access to the data in the FITS file. We use a library called DKIST, which I am eternally grateful exists and that I found it, because if I'd had to sit down and written this from scratch, I wouldn't have a demo for you, and I probably would be hugging my knees in a corner somewhere. DKIST is phenomenally good at doing many things. The main thing that I'm using it for is a way of creating an array from a load of pointers to FITS files. So when you access some data in the array, it will open the FITS file it needs to get the data out, pull the data out, and return it to you, and do whatever you want. I've got some demos for that in a minute. DKIST also has a lot of different scheduling capabilities, so it will run multi-process, multi-threaded on your local machine, or you can point it at an entire HPC cluster or cloud computing resources, and it will distribute it over as much as you've got. At the SciPy conference I went to last year, I loaded 12 hours of full resolution, all the wavelength passbands, AIA data, into Google Compute Cloud, and derotated and stacked them all in 45 minutes using 1.2 terabytes of RAM on Google Compute Cloud using DKIST. And it was just like magic. So the idea of providing it in DKIST is mostly to make my life easier, but there is a lot of side benefits of if you've got a lot of computing resource that you want to throw at DKIST problems, you should be able to do it relatively easily. So you've seen this before. This is just the representation of the DKIST array. So if we do something to this array, so if we square root the array, that happens almost instantaneously. It has not opened all of the FITS files and calculated the square root of every pixel in all of those FITS files when I ran that line, or else it would definitely still be going. So if we take that square rooted array and we slice it down to a single element, so just one pixel at one point, and then we run compute, it will then compute that one pixel. So in doing that, it's opened one file, read one pixel out of that one file, square rooted it, and returned it to you. And all of the other stuff just hasn't been touched. The cool thing here is that we can actually see what this has done. So it's taken the array, it's got a function, and then sliced it and got one result back. This isn't massively interesting. So what I instead have is another test data set, which is only 11 by 128 by 128, which makes this a little easier to do. If you try and visualize really large DKIST arrays, it takes a very long time, and you end up with a very, very large graph. So if we slice off the edges here, and then find the minimum of everything that's left, we now have an array which is just 128 by 128, because we collapsed the first axis. And if we compute it, it gives us back the actual array values. And if we visualize this and zoom out, we have these 4 files down here have not been opened because there's nothing above them. And what DKIST has done is it has calculated how it's going to find the minimum value. It's opened these 7 files and found the minimum of each one, and then found the minimum of that side and the minimum of that side, and then found the minimum and worked its way all the way back up to the top. So this underlying magic is how DKIST manages to distribute stuff. Because if you have this if I had 7 cores, it could do each one of these individually, send one piece of information back, and then return you one result to the process. Now that's the array. The idea of DKIST, by the way, is if you are familiar with NumPy, it provides a NumPy-like array interface. So in theory, in most places where you can use a NumPy array in Python, you can put DKIST and it will work. And it will do all of that underlying magic for you without you having to worry about it. So the second part of the ASDIF file and the dataset in general is that, in this case, 5-dimensional array has a coordinate system attached to it. Obviously, the pointing is as good as the telescope gives us, so there's fine alignment problems and stuff like Ryan was just talking about. So in the level 1 data, this is going to be as good as the telescope provides us information with, and all of the anything else the calibration has done through that process. But when you open a data set from the ASDIF file, it loads this GWCS representation of the coordinate of that thing. GWCS, hands up who knows what WCS is, just in general. Okay, WCS stands for World Coordinate Systems. It's frequently associated with FITS WCS, which is a standard of how you encode physical coordinate systems in FITS headers. The FITS WCS spec runs to about 5 papers and hundreds of pages and is a complete nightmare. But it allows you to encode spectral axes, spatial axes with different projections, all manner of different coordinate systems in your FITS header. And then there are lots of standard tools that read those headers and give you coordinates as well as data. GWCS is a different approach. It was written for JWST because they have a lot of IFU data and they represent their entire IFU calibration pipeline as a series, as one GWCS. So they go from like raw IFU all the way through to calibrated using GWCS, which is magic, and I have no idea how they do it. But it allowed you to represent way more complex world transformations than FITS WCS, but the main reason I use it is because it serializes to ASDIF. So the important thing is that it lets you calculate the world coordinate for a given point in your array. This is a representation of the 5D WCS for this VTF-like data set. The first 2 axes here are the latitude and longitude spatial axes. So you have a shift. The center point of the sun is at that pixel coordinates. There's a pixel scaling. There's a rotation. There's the tan projection, and then the rotation into the coordinate system based on the reference pixel. Then there's 2 linear axes, one for wavelength, one for time, and then there's a lookup table for Stokes. I won't go into this too much because I will bore you all to death. So, as I showed before, this is the 5D dataset, and when you slice it, like we did to get the array earlier, it also slices down the WCS. So this is now a WCS that only has 2 axes, which is just the spatial axes. So we've picked the first Stokes profile, the I profile, the first time wavelength scan, and the 10th wavelength point. And now we have a spatial coordinate system. So we can say what is the spatial coordinate of the 400 by 400 pixel, and it returns this AstroPy coordinate object. There's a bit going on here, so I'll walk you through this slowly. We have a SkyCoord, which is how AstroPy encodes physical coordinate systems. It's in helioprojective HPC coordinates, which are your standard like solar X, solar Y coordinates. It is taken at a given time. It has a given radius of the sun, and it has an observer position, which in itself has a time, slightly redundantly, and this is the position of the observer in the heliosphere at that time in heliographic coordinates. And then that is the actual physical coordinate on the last line there. So this is the 400 by 400 pixel is 410 arc seconds by 476 arc seconds. This SkyCoord coordinate object, these frames are implemented in SumPy, by the way. Lets you transfer between coordinate systems, so you can transfer it to heliographic coordinates like latitude and longitude on the sun. You can also, if you fancy it, transform it to like ICRS, which is an astrophysical coordinate system for points on the sky. I think you can also, I don't know. You can do like equatorial coordinates and lots of other different things as well, assuming you tell it where you are. So we can pick out a different larger cube. So this time we've just picked out Stokes I and left all the other 4 axes in, and it returns you a series of objects. So it's returned a time object, which like knows what scale it's in and uses 2 double precision floats to represent time. So it's got like a nanosecond in the lifetime of the universe accuracy in AstroPy time or something. It knows what the wavelength is, and the wavelength has a unit attached to it. It knows it's in nanometers because that's the real unit for wavelength. And then it has the coordinate point as well. And this is a bonus one. Here I have sliced out 4 of the 5 axes. For people who understand how WCS works, they will appreciate that this is interesting. So we have 1 pixel axis, but 2 spatial axes left, right? We've picked out 1 pixel, or 1 column of pixels here, but each of those pixel points have both longitude and latitude on the disk of the sun, right? So we can ask it for 1 of those pixels in that slice, and we still get back both longitude and latitude, because otherwise you could be anywhere. Right, plotting. What am I doing for time? Yeah, we're going to have an early lunch. It'll be good. So if we, come on. Why are you not? Boo. There we go. So this is all using matplotlib underneath and WCS axes in AstroPi. So we create a figure, we slice down the data set. Again, we're picking the 10th wavelength point. So this is returning a 2D data set. And then we plot it, and we get a plot. This looks vaguely like the surface of the sun. I'm reliably informed. I was a solar physicist once, but I also live in England, so I never get to see the sun. So you have latitude and longitude, solar X, solar Y. And as you mouse over this, it tells you what your well coordinates are on the image. You can zoom in, see what's going on. This is standard matplotlib plot underneath. Run through the Jupyter notebook, which does make it a little slower than I'd like it to be. But I most definitely have not got onto optimizing this yet, by the way. So if things are slow, they hopefully won't be like that forever. So here what I'm doing is selecting all time. So this Stokes I, all time, the first wavelength position, and the 500th row column of pixels. This one does take a little while to load because it has to read 128 FITS files to generate this plot, right? So it's currently opening 128 FITS files and reading 1 column out of each one. And when it gets there, it's taking a very long time. There we go. We now have a longitude time plot. The spatial, all of the axes, the physical axes on this I made up, by the way, so don't take too much stock in the fact that this is a like 60,000 second long data set. So this is, your X coordinate versus time. Again, if you mouse over, it tells you what coordinates you're in, and you can zoom in and interrupt the plot, as you can with matplotlib plots. What's this one? This is the same kind of thing again, except this time we are selecting all wavelengths for the 500th row. So we have wavelength along this axis and latitude along that axis. So you can see like the absorption line, or you might want it the other way around, but I'm not going to attempt to flip it around because I would guarantee that'll break for some weird reason that I don't understand. Right, questions on that before I move on to download, which is its own hell? Yeah.
Yeah, I was just wondering with the WCS that attribute, can you access that as like a dictionary to extract data from it? So say you wanted to know how big one of the pixels was in arc seconds for some reason, would you be able to do that, or would you need to access the header information directly?
Yes. So the question is, can you extract like some of the information out of the WCS, like the pixel scale, for instance, or other properties of the thing? Not in like a dictionary form. So the way that GWCS represents the WCS is as a series of AstroPi models. So you could go in and introspect those models and see the values, the parameters that all those models have. So the information is there, but it's not like as simple to get at as like a FITS header in that case. Yeah.
be incorporated in something like SunPy, or will they be their own separate thing?
Yeah. So the question is, will the user tools be incorporated into SunPy or separate? They use a lot of SunPy, but they will probably be distributed as their own package. But you need SunPy for them to work. So. Okay. So one of the other things that we have tried to do with the user tools, this is a relatively recent addition, is allow you to not have to download an entire data set. So when you search the data center, the minimum unit of search results is a data set. So you get, as Alistair described it earlier, like one instrument, one passband, etc. And like that is the granularity of the search results that you will get from the data center, right? So you won't be able to ask the data center search portal for just 10 seconds of a 3-hour-long data set. You will get back the 3-hour-long data set as your search result. So what we have tried to do in the user tools is allow you to like circumvent that restriction so that once you've got the data set in an ASDIF file on your computer, you can only download bits of it if you only want to download bits of it, right? Because if you only care about 10 seconds and the data set is 3 hours long and 5 terabytes, you probably don't want to transfer it all. And we don't want you to transfer it all because that's our bandwidth and other things as well. So I have this ASDIF file. As I said earlier, dataset search doesn't exist in the user tools yet, so I have magicked this ASDIF file onto my computer. But the idea is that you will also be able to search for these through the user tools. And this gives the same object that we had earlier. But this has no data attached to it. So there's that. It references 9,000 odd files, but we haven't got any of them. If we subset this data set, say we only want to download one wavelength scan out of this big data set, so we're going to transfer 19 of the 9,700 files, you'll be able to do that with this download method here. I'm going to take a slight aside at this point. So as Alistair mentioned earlier, the download is done using a system called Globus, which is also how you will log into the data center if you want to get embargoed data or embargoed search results. You will not have to be, the idea is that you will not have to log in to download, to search if you don't care about embargoed results. And you probably won't have to log in to download the ASDIF files. So the idea is, although there's no guarantee of that at this point, that if you're searching for public data sets, you'll be able to get this far without logging into Globus, right? As soon as you want the FITS files, you will have to log into Globus. So the first thing that I'd need to do if I want to transfer some data is I need to start Globus. So I'm going to run this Globus Connect thing. This pops up this little window, and I click Connect. And this has started a Globus endpoint for me to download stuff on my laptop here. I would be remiss, Tony will tell me, this system is still very like development at the data center. It is not got a 40 gigabit link out of the building or even in the building at the moment, so performance is not representative. When I run this cell, it will tell me to go here and log in. Turns out to be a big quirk of Jupyter Notebooks that it can't open other web browser tabs, even though you're in a web browser, so you have to click the link yourself. Type in something in this box and press enter, and it logs me into Globus. And now it has started my transfer. So we've got 20 files. We are 0% of the way through transferring it, and we've got 20 files. You now see that this light on the Globus endpoint has gone green, and transfer is active. Globus only refreshes its progress every so often, so in about another 20 seconds or so, this bar is going to go to fully finished, because I'm only downloading 20 files. So I've started this. There you go. It's idle now, so there we go. It's finished. We have downloaded 20 of the 20 files in 39 seconds. So I've run this endpoint locally on my machine, but you can also, your university compute cluster might have a permanent endpoint that you could direct things to. If you do have a Globus endpoint somewhere else, you can just do like endpoint and tell it where you want to send it in this download function. So if we go back here, so I've now downloaded those 19 files onto my computer into this path. If you specify this path, the Globus does actually have to be able to write to that path. And now we can plot that partial data set that we just downloaded. Ding. So again, this is a space-based plot. It knows what the world coordinates are, and we can like step through the wavelength. Each time it refreshes this plot, it's opening the FITS file and reading the data out of the FITS file every time it loads it. So it's, I think it will cache them as well, but like it is not opening any of the files until it actually has to plot them. So now that I've got that set of files on my machine in a different place, I can construct a data set from that directory. I have to do it this way to demo it because the way I want this to work doesn't exist yet. But at some point you'll be able to reload this data set at a later date, and you get this new DS is the 5D data set like it was earlier, except now we've only got 19 of the files, not all of the files. So if I make this plot, which is Stokes I, all time, all wavelengths for one space pixel. This is attempting to read all 9,700 files, right? We're plotting all time for all wavelengths. So this is looking for all of the 9,700 files, but only 19 of them exist. Which does lead to the question why it takes so very long, because it's actually only opening 19 files, but I definitely haven't had a chance to work out why that is yet. Given a minute or several. It always feels longer when you're standing in front of people just waiting. Okay. So this is wavelength and this is time, and you can see that we have one scan, right? All of the other data doesn't exist on disk, so it's just blank. But you can still like zoom in and see what's going on here and stuff. There we go. And here are some links. So this package is already open source. If you're crazy, you can watch me write it. This is the repo that has this notebook and the data and the ASDIF file and stuff in it, if you fancy that. There's also the notebook, and a PDF version is in the Google Drive folder with links to these other things. I also work on SumPy. I have bought some SumPy stickers with me. They are at the back if anybody wants some SumPy stickers. There's also this other SumPy project called NDCube, which is what I'm basing this stuff on. So if you are using high dimensional data that has world coordinates attached to it, so like iris data or Anode data where you've got actual headers, and you fancy using them in Python, you could try out NDCube and get some of similar kind of plots to the ones I've showed you here, if you fancy that. There's a chat room if you want to talk to me. I'm normally in that chat room. So that's the end, like 40 minutes. Yes, Fraser wants me to tell you that since Alistair's talk started this morning, the data center would have downloaded over 1 terabyte of data. Yes.
Have you started playing with spectrographic data? You showed mostly even spectroscopy, CDF type. But something like this, since basically would be
First, yes.
the first, and all the
A little bit. I haven't. Yeah, I could do with. I've never used that kind of data myself. I've never used any of that kind of data. I've never used any data by myself. I wasn't never an observational solar physicist. So like use cases for that kind of thing is something that I'd like people to tell me. As I say, the tools aren't quite in a place where you can probably easily get them and start using them yourself yet. I hope that will not be the case in 2 or 3 months' time. But I'm attempting to read that data you gave us the other day and start playing with it. I mean, I'm also, the user tools deliberately don't do much with the data, right? They represent the coordinate system, get the array, and allow you to do some kind of plots. So I'm hoping that the user tools won't really care too much about how the data came to be. It will just expose that to you so that you can.
Sure, but there is, the details that you have to remember for one instrument are different than the details.
Sure, yeah. So for instance, I don't have a good answer yet for the time and space on the same axis of the array. SumPy has a Google Summer of Code student working on NDCube this summer, and I'm hoping that they will provide me the answers to that problem. So.
Are you talking to the IRIS people?
So NDCube actually came into being motivated by Iris. I'm on camera, aren't I? Yeah. So it does work with Iris data, and the idea is that it will support all those different kinds of data sources at once. Yeah.
Something that maybe you have said it, but maybe I don't. Like, the data is I don't know, I mean, searching through the data is a lot of work. Even though it is in an embargo, you're searching the data cube that is useful for you. I don't know, it can be embargo, but in 6 months, that will be useful. So I will be able to search the metadata before the data gets released?
We don't know. There has not been a policy decision made on whether metadata is embargoed along with the data or not. So I don't know is the answer to that.
The data center is capable of doing it either way.
Yeah.
But it's a policy decision for the observatory as to whether we are.
But yeah, so if metadata is not embargoed, only the actual arrays are, then you will, and if it is, then you won't.
I mean, you're searching the correct data as you have presented is will take months,
Yeah, so Alistair kind of touched on this earlier, like the list of stuff that you'll actually be able to search against is basically things derived from this list of files. Like this is the list of information that the data center has available for you to search against. I'll be exposing it through like SumPy's search interface where you can search for things like instrument and wavelength and time and whatever else. But then the idea is the ASDIF files will allow you to do more complex local search once you've got those, if you want to narrow it down to really specific things.